This presentation on the refrigeration lab is by Mitchell Garrett, Joseph Ganina, Joseph Heaton, Youngji Lee, and Shashank Narayan.
This lab group was asked to test the vortex tube cooling system on behalf of a company. We were to investigate how input pressure affects various output characteristics of the system. Once done, the group was to use its understanding of heat transfer processes to determine the mass of a local block being used as a load and of the thermal resistance for its encasing insulation.
Pressurized air was pumped through the system shown here. A vortex tube is used to create a hot and cold output from ambient temperature input. We measure the temperature and flow rate at various points in the system and across a range of input pressures. Here we have plotted the relationships between the log of pressure and the log of temperature at T4 hot and T4 cold locations. These are the hot and cold exits of our vortex tube. A relatively linear relationship is observed between the change in temperature from ambient and an increase in pressure. In other words, as pressure increases, the hot output gets hotter and the cold output gets colder. The rate of change of temperature with respect to pressure increase is greater for the hot output. This is shown by the slope of the equation for T4 hot being over twice the magnitude of the slope for T4 cold. The same analysis was applied to pressure versus the flow rates at our hot and cold locations. Mass flow rate increases with increased pressure in both situations. What can be seen is the starting value for the cold mass flow rate is higher than that of the hot. At the same pressure, the mass flow rate is higher for the cold output than the hot. Also, as pressure increases, the difference in mass flow rate becomes larger due to the larger slope value in the equation describing the cold mass flow rate.
Thermal resistance was found experimentally using the thermodynamic energy balance across the block. Comparing the heat transfer rate of the fluid's flow to that of the ambient heating, an inverse relationship was determined by averaging data across the 50 psi and 80 psi steady-state loads. This value is approximately 2.32175 Kelvin seconds per joule. To determine the feasibility, we compared that experimental to a theoretical resistance determined by a provided equation. After measuring the 5 blocks comprising the insulating styrofoam piece, we tabulated the contact area and block thicknesses associated with the resistance. Using the known insulation thermal conductivity of 0.033 joules per second meter Kelvin, we found an R theoretical of 29 Kelvin seconds per joule. This large discrepancy, almost a factor greater, was likely due to imperfections in the material, exposure to the ambient air, and contact with an insulating adhesive.
So the temperature of the block is going to decrease exponentially over time. And that relationship of the temperature xt is given by the system cooling equation. There are two constants that we need to find for this cooling equation. Those are B and tau. In order to find these constants, we need to take the natural log of the cooling equation, and then that will linearize the equation. Because it's now linearized, we can use York regression to determine tau and B as well as their uncertainties. Given the uncertainties in our temperature and the uncertainty in the measurement of time. The slope of our linearized equation will be negative 1 over tau, and the intercept will be the natural log of B. And then we're going to compare the 50 psi and the 80 psi test cases. So here we can see the cooling rate for the 50 psi and the 80 psi cases. As you can see from the graph, it appears that the 80 psi case will have a much faster cooling rate than that of the 50 psi. This is because the increased pressure is going to drive more working fluid through the system. On the left, you can see the taus that we calculated as well as the b's that we calculated with their k equals 2 uncertainty. One thing that I will note is that the equation for the cooling rate does not quite match up for the 50 psi case. This might be because we stopped the experiment slightly too early before T block reached a steady state temperature.
For mass computing, we assume all heat into air is coming from the block, and it means heat transfer rate due to ambient heating is zero. So the energy change rate of mass is equal to energy change rate of air. In order to calculate mass of the block, we need to find derivative of the temperature of block, and it is equal to B over T times exponential negative T over tau. And we've found tau and B values from the cooling rate part. According to the equation, experiment mass of the block is slightly lower than measured mass, which is because there was unexpected heat transfer through the conduction. It caused underestimated heat transfer.
In summary, we found that the cold temperature exiting the vortex tube has a negative correlation with the increase in pressure. On the other hand, the hot temperature shows a positive correlation. Moreover, our R experimental value was off by a factor of 10 from our theoretical value. The thermal resistance of the low block was a lot less than what we had expected and can be attributed to a portion of it being exposed to air affecting its overall resistance value. The cooling rate of 80 psi is faster than the cooling rate with 50 psi due to its lower time constant value. Lastly, the experimental effective mass of the load for 50 psi has an experimental error of approximately 3.6%, and the experimental effective mass of the load for 80 psi with its uncertainty was found within the range of the measured mass value of 0.4825 kilograms. Thank you all for listening. Any questions?